Here we have pre-built subassemblies to demonstrate the variation of stress through the cross-section of a circular beam due to a torsion load. For this demonstration, we will consider a solid and a hollow beam, both subjected to a torsion load. Both beams have the same cross-sectional area and length. They are composed of the same material. We will run a static analysis in Apex and compare the stress and deformation induced in the beams due to the torsion load. As in the previous beam demonstrations, each subassembly consists of the beam, a part used as a tool to apply the load, and a block on which the constraints are applied. For each subassembly, the beam, tool, and block are glued together. In both beams, we apply a 1 Newton force on the tool in opposite directions to induce a torque in the beam. With a moment arm length of 0.10909 meters, this translates to a bending moment of 0.218 Newton meters on each beam. To run the analysis, right-click on Assembly 1 in the model tree and select Set Analysis Context. When the status bar reports that the model is ready for analysis, click the Running Man icon to start the analysis. The simulation has completed successfully, so let us look at the stress in the solid beam. Click on the Post Process icon and under the Post tab, click the empty box for Assembly 1. This hides all subassemblies. To display only the solid beam, scroll down and check the box for Solid Beam. Press both mouse buttons simultaneously to fit the model to the screen. By default, the deformed shape is displayed. To view the shear stress on the beam, click the fringe icon and in the spectrum area change the derivation to maximum shear. Notice that this value compares to the theoretical value of 17 kilopascals. Notice the stress distribution. The highest shear stress in the beam occurs at the outmost section and drops gradually as we move inwards. Hide all subassemblies, display only the hollow beam, and fit the model to the screen. Again, observe that the Apex results compare with the theoretical value of 8.9 kilopascals. Now let us compare the total section rotation of both assemblies in a front view. Click on the x-axis of the triad and fit the model to the screen. Notice that although the beams have the same cross-sectional area, the hollow beam rotates less than the solid beam.